Okay, section 2.4 is on complex numbers. 2.4 is not on the quiz tomorrow. I'm pre-teaching, you'll have a quiz tomorrow, then you'll have time to work after your quiz on this. So, complex numbers. All along, we've been talking about two things that we cannot do in the real number system. We can't divide by 0, breaks the law, and we can't take a square root of a negative number. Okay, and we've been avoiding that all this time. Today we're going to add those complex numbers in so that we can do those things. So, first of all, we have this lovely imaginary number that you know from Algebra 2 called I. And it is defined as the square root of -1. So when we have something like x squared plus 4 equals 0, and we're trying to solve that, and x squared plus 4 equals 0 can now be solved. Because we can bring that 4 to the opposite side. And when we take the square root of both sides, we can call this x. And we have to remember that when we take a square root, it's always plus or minus in Algebra 2 and pre-calc. We don't just drop the negative like we did in geometry because we were primarily talking about distance there. And we can rewrite this as the square root of 4 times the square root of a -1. We know the square root of 4 is 2. And we know that the square root of -1 is now this guy called I. The standard form of a complex number is a plus bi. A and b are actually real numbers. I is the imaginary part. So this particular case, I have two imaginary numbers here. I have a 0 plus 2i and a 0 minus 2i. A in this case is 0 and b is 2i. So one of them is a -2i and the b is 2. So one of them is a -2i and one is a positive 2i. So we have to remember how to solve those kinds of equations and how I works its way through the process. So we defined the square root of a -1 as I. That means that when we are squaring I, we're really taking the square root of a -1 times the square root of a -1. So the square root of a -1 squared becomes simply -1. Anytime you take I times I, you're going to get a -1. Okay? I cubed is I times I times I, or -1 times I, -I. I to the fourth is I times I times I times I. So you could take -I times I again, and that's going to be a -I squared, but I squared was a -1. -1 is a +1. And the pattern continues. Nope, this should be a -I. So whether you put a little table in the top of your notes and just review that table every so often till you can commit it to memory, that's okay, but you can derive it as well by simply just multiplying the previous one by I, and then the next one by I. Okay? So we can do things like ask you, what is I to the 5th? -I. Okay? No, not -I. Just plain old I. Why is it just plain old I? Well, it's going to repeat the pattern, right? If I take a 1, I to the 4th times an I, 1 times I is I. Okay. I to the 6th says take that times I, and what are you going to get? -1, because I times I squared is a -1. I to the 7th, -I. I to the 8th, +1. And it repeats the pattern. So what would I to the 16th be? +1. Anything divisible by 4 is going to be a +1. Okay. I to the 7th was supposed to be a -I, if I'd write it well. Okay. I to the 5th was I, yep. So what's I to the 25th? I. Why? It is divisible by 5, but don't think of it that way. Think of it as always dividing by 4 to get rid of the extras. 25 divided by 4 is 4, remainder 1, right? If our remainder 1 is 1, then it's like having the first one in there. Okay? What would I to the 53rd be? Hearing -I. 53 divided by 4 is going to be 1, 3, remainder 1. Remainder 1 says I. With all prime numbers. No. What about it should follow in patterns of 4. Okay. So look for your remainder. Divide them out. Look for your remainder. This remainder 1, 2, 3, and no remainder. Okay. All right. Operations with complex numbers. Similar to good old Algebra 1. You're going to combine like terms when you're adding. Okay? 6 minus 3i plus 2 plus 2i. Add your like terms. Add your reals. Add your imaginaries. And if you don't want to write them in parentheses, that's okay. They've just been grouped. So 6 plus 1, 7. And -3i plus a +2i, -I. The complex number 5 minus I minus the complex number 2 minus 4i means we have to do what? Subtract. And I would likely distribute my negative through, right? So plus a -2 plus a +4i. Of course, it's going to do the same thing as yesterday. Eraser does not want to work. So 5 minus 2 and -I plus 4i. Okay. Multiplying. We can multiply a real number times a complex number or a complex number times a complex number. When we multiply our real number through, it's just a distributive property. 2 times 14. 2 times a -3i. Easy enough. When we're multiplying two complex numbers together, what do you think we need to do? FOIL it out. 2 times 4. 2 times 3i. Negative I times 4. And negative I times a positive 3i. Negative I squared, 3i squared, and I squared is negative 1, so negative 3i squared is the same thing as positive 3. Combining your imaginary parts and your reals, 8 and 3, and then 6i and negative 4i. Okay, next we have a complex number that's being squared. 2 plus 5i quantity squared. What does that mean? So when we square the 5, so what most of the time people want to try to do is square the first, square the last, and call it good. What's wrong with that? I squared is negative 1, so they're going to say that this is 4 minus 25, or a negative 21. What's wrong with that? Is x plus 2 quantity squared the same thing as x squared plus 4? We need to write it, we have to FOIL it out, don't we? I don't know if this is going to erase. Of course it's not. So we have to write this as 2 plus 5i times itself. So we lost our outside and our inside terms. Outside gets me 10i, inside gets me 10i, so I will actually have a negative 21 plus 20i. Okay, so don't forget to FOIL that out. These guys are called complex conjugates. Talk about them just in a moment. But notice what's going to happen here. 3 times 3, outsides, insides, and lasts. Insides went away. Negative 4i squared becomes 4. 9 plus 4. When they're identical except for a change of sign, and we multiply them together, the imaginary part goes away. We just have the real. Okay? Complex conjugates are of the form a plus bi and a minus bi. With polynomial equations, they travel in pairs. When one's the root, the other's also a root. And the nice thing about them is their product is a real number. Because of that, we can do something called rationalizing the denominator. One of the things we told you in Algebra 2 is that we don't like to have a radical in the denominator. Isn't I the square root of a negative 1? So that's got a radical in the denominator, doesn't it? What did we do to something like this to make the radical go away? Multiplied it by the square root of 3, but we can't just introduce the square root of 3 in the denominator. We had to put it in the numerator as well, so the net effect was multiplying by 1, and we ended up with 2 square roots of 3 over 3. Same process here, but we don't want to multiply by 2 minus 3i. We want to multiply by its conjugate. So what are we multiplying by? Yep, 2 plus 3i. So denominator will get a 4 minus 6i plus 6i. You're pre-calc students now. You don't have to show that step if you don't want to. But last times last, negative 3i times a positive 3i is going to be negative 9i squared. So plus positive 9, and 9 and 14 is 9 and 4 is 13. Suddenly got 14 out of there trying to say 13. Okay, let's work on the numerator. 6 times 2. Outsides, 6 times 3i. Insides, 2i. And last, I times a positive 3i. 3i squared, which is negative 3. Combining my real parts, 12 and 3, a negative 3, and 18 and 2i, 18i plus 2i. Does anyone need to see the second one worked? All right. So now we can solve things like x squared plus 16 equals 0. Or x squared plus 6x plus 24 equals 0. I showed you one similar to this, x squared plus 4, a little bit ago, right? Do you need to see this one worked? Yes, no? Yes, okay. So we're going to solve this. That means that x squared will be equal to a negative 16. We bring the 16 to the opposite side. And then when we take the square root of both sides, the square root of x squared is x. The square root of a negative 16 is going to be what? Plus or minus 4i. Skipped a bunch of steps there. Square root of 16 is 4. The square root of a negative 1 that was taken times that 16 is I. And whenever we take a square root, we have to remember that we can have both the positive and the negative roots. They will both satisfy the equation. Okay. So solving this, and we're going to throw a little completing the square in as a kind of a review, because we started out by completing the square to find the vertex of our parabola in this chapter. So I want to solve x squared plus 6x plus 24 by completing the square. How did we do that in section 2.1? Yes, Austin. Half the middle term squared. Half of b squared. Half of 6 is 3. 3 squared is 9. But I added 9. There's no leading coefficient here. So in order to balance the equation and keep it the same, I have to subtract 9. So this is now x plus 3, quantity squared, and 24 minus 9, 15. That was equal to 0 before, right? So we don't want to lose our equal 0. So what can we do? subtract 15. Take the 15 to the other side because we want to eventually isolate this x squared, or this x plus 3 quantity squared. So if we take 15 away, we'll have an x plus 3 quantity squared is equal to a negative 15. Now what? Foiling it would get us back to where we were. Square root, yep, so we'll square root it. When we square root both sides, this is going to be x plus 3, and this is going to be plus or minus I square roots of 15. 15 is 3 times 5, right? There's no perfect square in there. Almost there. What do we have to do yet? Subtract 3. So x will be negative 3 plus or minus I square roots of 15. There's my A, there's my B, complex number, actually complex conjugate. 3 plus I squares of 15 and 3 minus I squares of 15. Everybody good? Assignments up there? One second.